And you're on.
Yo, what's going on, guys? It's another Porter podcast here. Let's get started.
Sweet. Yes, he's a professional. Okay, now, last lap. Yesterday. Yeah, yesterday. We were making solids. What were those solids called? Precipitates. Now, those precipitates were the result of something being insoluble in water. So, what are we using right now to determine what's soluble, what's insoluble in water? No. You guys recall?
Oh, the chart.
The chart? Yeah, where's that chart? Oh, right before it. You guys recall the solubility table?
Yes.
Yeah. So, we have the solubility table that tells us what's going to be soluble in water and what's not. Your lab, you always started out with two things that were soluble in water. How'd you know that? How'd you know those two things were aqueous? What'd you observe? The two bottles? What was in the two bottles? What stuff?
Liquid.
No, not liquids. You observed they were aqueous solutions. That's how you know your two reactants in all of that lab, every time you picked up two bottles, they were aqueous because you observed they were solutions. So we mixed two aqueous solutions together, and out of all the combinations, you guys were trying to figure out which combinations provided you an insoluble substance or a solid. So, take a look at this reaction. You guys have seen this several times. Lead 2 nitrate reacts with potassium iodide to produce a precipitate of lead 2 iodide plus potassium nitrate. The question I have for you is, how do you picture the reactants here when they are in the solutions? What do you picture? You have the solution right here. If this is your solution, imagine this bottle of water. The water inside is your solution. How do you picture the reactants inside this solution? That's what we're getting into today. That's what I want you to take away today. So, take a look. If we have lead 2 nitrate solution, I want you to picture this as Pb plus 2, aqueous, and 2NO3 minus aqueous ions. So in a container of lead 2 nitrate, all you have is water, Pb plus 2s, and NO3 minuses all floating around in that ratio. For every one Pb plus 2, I have 2 NO3 minuses. They're all floating around in the solution. So you have your water, and then you have all these ions floating around. Now, what happens if I put some potassium iodide into that solution? Now what do you have? What ions? K? What's the oxidation state of K? Look on your periodic tables. You should see it's in group 1, +1. What about the oxidation state of I? I minus. So you have 2 Ki, so you have 2 Ks, 2 I minuses. They're both aqueous in state. So when we combine these two solutions, what you have are all these ions floating around the solution. Now, if all these ions are floating around the solution, what do they have the opportunity to do? What? Yes. They can bond, but they have to interact. So if you have them all in the same solution and they're all interacting, this Pb plus 2 is able to interact with 2 I minuses And we know from our demos and our lab that when Pb plus 2 reacts with 2 I minuses, what results? What is that? Lead 2 iodide, but what results? What do you remember about lead 2 iodide? No, it wasn't brown.
Or did it make the white speck?
It didn't make white specks.
Yellow.
Was it yellow?
It was the yellow stuff. The yellow solid, the yellow precipitate that formed. Remember, 2 clear solutions? I used an eyedropper and I dropped in a little bit of the second solution into the first, and then you had that yellow precipitate. That yellow precipitate stood out so well because they was coming from 2 clear colorless solutions. So, here we form lead 2 iodide solid. So PbI2 solid is now in your solution, floating all around. The yellow precipitate. And what else? What happened to the potassium in the nitrate? Well, if we write out the rest of this reaction, we have PbI2 solid plus, what's going to happen to the K plus? It stays in the solution, aqueous, and NO3 minus, aqueous. What results is your precipitate and your NO3 minus and K plus, they stay the same. They're just floating around still. So, altogether, this reaction right here, where I show all the ions that are floating around in this solution, this is called an ionic equation. So, this is your ionic equation. Yes?
Okay, so if like PB and I are like
Now, what is happening to the potassium and the nitrate in this reaction? What are they actually doing? Look at the start in the reactants and look at the products. What is different? What's different? What's different? Look at nitrate right here and look at nitrate right here. What happened to it? It's kind of a trick question. Like literally, what happened to it? It's floating around right here. 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 Nothing happened to it. What about potassium? Floating in your solution, still floating in your solution. Nothing happened to potassium either. It started out as an ion, it ended as an ion. We call these spectator ions. What are they spectating? The what? What bonding? The what? What's bonding here? Literally, what is changed on your product side? The lead to iodide. The lead and iodide. So you are literally having potassium and nitrate watch the whole reaction occur. I can actually rewrite this as Pb plus 2 aqueous plus 2I minus aqueous, and they react together to form PbI2 solid. This is called my net ionic equation. My net ionic equation. What's the difference between my ionic equation and my net ionic equation? There's my ionic. Yeah. So for my net ionic, I just get rid of anything that's not doing anything. The only thing actually happening here is my lead plus 2 is reacting with my I minus. I get rid of everything else. This is my net reaction. This is what's happening. But my net ionic equation does not include my spectators. The spectators, I leave out.